Have you ever played on a swing and felt yourself go back and forth? Or have you seen ripples on water when you throw a small rock? Do you know why those things happen? Well, today we'll learn something cool about that. It's called oscillatory motion and waves. Before we delve into the lesson, let us first define the objectives. At the end of this lesson, you should be able to: first, explain the differences of the different types of waves and motion. Second, solve the characteristics, amplitude, wavelength, period, frequency, and intensity of a wave. And lastly, relate the importance of waves and motion in daily life. So now, what is oscillation? Oscillation is a wiggle in time. To better understand this, when something moves back and forth again and again, that's called oscillatory motion. Like when a swing moves front, then back, then front again, it's repeating the same motion. An example is the periodic motion of a pendulum where the bob swings back and forth. Now, what's a wave? Wave is like a little wiggle that moves through space or air. For example, when you throw a stone in water, you see round ripples. Those ripples are waves. Some examples are sound waves, waves on a string, and electromagnetic waves. Now that we've already known the difference between oscillation and a wave, let us now move on to the periodic motion and frequency. Periodic motion is a motion that repeats itself at a regular time interval. When something moves again and again and again, we can count how fast it moves. Frequency is the number of events per unit time measured in hertz. If it moves fast, we say it is high frequency. That means it wiggles a lot in 1 second. The period is how long it takes to finish one wiggle or one swing. Here's the equations. To better understand the topic, here is an example. Calculate the frequency and its period if a pendulum completes 40 cycles in 20 seconds. Let us first identify the given. We have a cycle that is equal to 40 and a time that is equal to 20. So since we are going to calculate the frequency and the period, let us first determine the frequency before we solve the period. So the formula is frequency is equal to cycle over time. And then substitute 40 and 20. Now we have the answer of 2.0 Hertz. We can now solve for the time. The formula of time is 1 over frequency. And then substitute the 2 in the frequency. Now we have period is equals to 0.5 seconds. Therefore, the pendulum's frequency is 2.0 Hertz and its period is 0.5 seconds.
Spring mass oscillator. So, it is a simple system in physics where a mass is attached to a spring. When displaced from its equilibrium position, the spring either stretches or compresses and exerts a restoring force on the mass, making it oscillate back and forth.
I know you might be confused, so let's break it down. So basically, a spring mass oscillator is a system in physics kung saan may mass na nakatouch sa spring. Kapag ginalaw mo siya from its normal position, the spring creates a restoring force na nagkukos sa mass to move back and forth. It's a good example of harmonic motion kasi it shows kung paano nagbabalance yung force and movement in a system.
Specifically, the equation we use to describe its motion. Basically, ito yung system na may mass na nakasabit sa spring. Tapos, kapag hinila mo siya at binitawan, it moves back and forth, or what we call oscillation. Now, the first one that we have is calculating the period, where you can read it as t equals 2 pi times the square root of m over k, where t is the time period measured in seconds. Yun yung time na needed for one full back and forth movement. Now, the next one is the 2 pi, and it is a constant, and it is read by 3.14159. And the next one is the m, it is a mass of the object in kilograms. And the last one is k, it is the spring constant measured in newtons per meter. It tells us how stiff the spring is. So basically, kapag mas mabigat yung mass or mas malambot yung spring, mas matagal yung period. So the second one is calculating the frequency. It is read by F is equals to 1 over T, and so frequency tells us how many cycles happen per second. Basically, kung gaano kabilis yung oscillation, it is measured in hertz. And lastly, we have the angular velocity. It is symbolized by the Greek letter omega, which is W, and it is read omega equals 2 pi times f. This measures how fast the object oscillates in terms of radians per second. So para siyang speed pero in angular form. So ayun guys, these three formulas are all connected, the period, frequency, and omega. In short, kapag alam mo ang isa, madali mo lang makuha yung iba. It's all about how the spring and mass move in perfect rhythm. That's simple harmonic motion.
Okay guys, so for example number 3, we're talking about horizontal spring with a spring constant or K equal to 300 newtons per meter and a mass of 0.75 kilograms attached to it. The problem says it's undergoing simple harmonic motion, so we need to calculate three things: A, the period, B, the frequency, and lastly, the angular velocity. So, the formula for the period of a spring is T is equals to 2 pi times the square root of m over k. Now, let's substitute. Now we have T is equals to 2 pi times the square root of 0.75 divided by 300. Solving that gives us the period of 0.314 seconds, meaning that's how long it takes for one to complete oscillation. Step 2. Frequency. The formula of frequency is F is equals to 1 divided by T. So if we substitute it, the frequency is 3.18 Hz, meaning it oscillates about 3.18 times every second. So for step 3, the angular velocity. The formula for angular velocity is omega equals 2 pi times f. So if we substitute them, we have 19.96 radians per second. So ayun, to summarize, the mass spring system takes about 0.314 seconds for one full oscillation, and it moves 3.18 times per second and has an angular velocity of about 19.96 radians per second.
Now let's move on to the physical pendulum. This one is any real object that swings, not just a small mass on a string. For example, a baseball bat that swings back and forth, or a disc twisting on a wire. When you push it back, a restoring force pulls it back, causing it to swing in a regular rhythm, just like a simple pendulum. Pero mas realistic kasi siya kasi may shape at mass distribution siya. And for the equation for the physical pendulum is T equals to pi times the square root of I over mgl. And the I is the moment of inertia. Basically, the mass is spread out around the pivot point. And m is the mass of the object, and g is the gravity, and L is the distance from the pivot point of the center of the mass. So if the object is heavier or its mass is distributed farther from the pivot, mas mabagal ang swing, but if it's lighter or closer to the pivot, mas mabilis ang oscillation niya. So in summary, the simple pendulum focuses on a point, mass, and string. It is perfect for basic models, pero ang pendulum naman, it applies to the real objects that actually rotate or swing. So they both follow the same harmonic motion principles, they just differ in how the mass is arranged.
Let's proceed to the three types of damping motion. Underdamped motion, a condition where an oscillator returns to equilibrium while gradually tuned. The system returns to equilibrium faster than an overdamped system, but it overshoots and crosses the equilibrium position multiple times. In simpler terms, this means the object still moves back and forth a few times before stopping completely. The movement becomes smaller each time until it finally settles at the center or resting position. For example, a child playing on a swing and a church bell ringing. When a child is on a swing, the swing doesn't stop right away. It keeps going back and forth several times. Each swing becomes smaller because of air resistance and friction. The same thing happens with the church bell. After being struck, it continues to move and ring several times before coming to rest. Both examples shows underdamped motion because there's still oscillation or repeated movement before the system. However, Underdamped motion. It refers to the slow movement of an object in a system which returns to equilibrium. It moves more slowly towards equilibrium than in the actual critically damped system. In simple terms, the object doesn't bounce or move back and forth. Instead, it just moves slowly back to its original position. It reaches equilibrium without overshooting, but it takes longer to do so. For example, a hydraulic door closer and a heavy old gate. A hydraulic door closer slowly shuts the door. It doesn't swing back, but it also doesn't slam quickly. It gently moves until it's fully closed. A heavy old gate also closes slowly because of friction in its weight. It doesn't swing back and forth. It just slowly returns to rest. That's why both show overdamped motion. Slow, smooth movement with no oscillations. Critically damped motion occurs if the object returns the system to equilibrium as fast as possible without overshooting. Like automatic door and window closure mechanism, they promptly come to their original position without showing any further oscillation. If the damping ratio is reduced beyond this limit, the system will begin to oscillate again. Simply put, this is when the system returns to rest quickly and smoothly without bouncing or going past the center point. It's the perfect balance, not too slow like overdump and not oscillating like, for example, car suspension systems, automatic doors. Car suspension systems are designed to absorb shocks quickly when a car passes over a bump. The car returns bouncing up and down. Automatic doors also close quickly and stop right at their proper position without swinging back open. This example demonstrates critically damped motion, where the system returns to rest in the shortest possible time, fast, stable, and without extra movement.
I'm here to discuss one of the most interesting parts of our topic on oscillatory motion, mechanical waves, including transverse, longitudinal, periodic, and sinusoidal waves. Let's begin with mechanical waves. A mechanical wave is a disturbance that travels through a medium, transferring energy from one place to another. It's important to remember that mechanical waves cannot travel through a vacuum. They need a medium like air, water, or solid materials to move. Example, when you drop a stone into water, ripples spread out. Those ripples are mechanical waves. The energy travels through the water, but the water itself only moves up and down, not outward with the wave. So in simple terms, mechanical waves are just energy traveling through matter. Next is the transverse wave. In this type of wave, the vibration of the particles is perpendicular to the direction of wave travels. Imagine holding one end of a rope and moving it up and down. The wave moves horizontally, but the rope itself moves vertically. That's a transverse motion. Transverse waves have crest and throws. Examples of transverse waves include light waves, radio waves, and waves on a string. Moving on to longitudinal waves. In this type, the vibration of particles is parallel to the wave's direction. A good example is sound. When someone speaks, their voice makes air particles vibrate back and forth, creating areas of compression and rarefaction. That's how sound travels through air, as a longitudinal wave. So to summarize, transverse is a motion that is going up and down. Longitudinal is a motion that is going back and forth. Both transmit energy, just in different ways. Now, let's talk about periodic wave. A periodic wave is one that repeats itself in a regular pattern, just like a heartbeat or a clock's tick-tock. Here are the important properties and formulas of periodic waves. Wavelength. It is the length of one full wave cycle. Amplitude. It is how high or strong the wave is. Period. It is the time for one complete wave. And frequency. It is how many waves pass per second. The formula is frequency is equals to 1 over period, and period is equals to 1 over frequency. Wave speed is how fast the wave travels. The formula is wave speed is equals to frequency times amplitude. So if you know two of these quantities, you can easily find the rest using these formulas. Example, if the frequency of a wave is 5 Hz and its wavelength is 2 meters, then its speed is V is equals to 5 times 2, then we get 10 meters per second. Now for sinusoidal waves. These are special because they follow a smooth and repeating sine curve. They're the foundation of many types of waves in physics, like sound, light, and water waves. The general equation for sinusoidal wave is this. Let me explain each symbol. So y quantity xt, it is the displacement of the wave at position x and time t. The A stands for amplitude in meters. K is the wave number. W, which stands for omega, is the angular frequency. And the weird symbol, which stands for pi, is the phase constant, which shifts the wave. T is equals to time that is measured in seconds, and x is the distance in meters. From this equation, we can get other relationships: period, frequency, wavelength, speed. So, in short, this formula helps us describe how a wave moves, how fast it travels, and how high it oscillates. Example, if a wave has a frequency of 10 Hz and a wavelength of 0.5 meters, then, using the formula, V is equals to frequency times amplitude, then we get 5 meter per seconds. So to summarize my report, mechanical waves transfers energy through a medium. Transverse waves move up and down perpendicular to their direction. Longitudinal waves move back and forth parallel to their direction. Periodic waves repeat regularly and follow formulas for speed, wavelength, and frequency. Sinusoidal waves are the smooth, mathematical version of periodic waves described by a sine function. In conclusion, waves are not just scientific concepts. They're part of our daily life. We hear sound through longitudinal waves. We see light through transverse electromagnetic waves, and even feel vibrations through mechanical waves. Understanding their formulas helps us see how energy moves all around us.